Thank you for the invitation to this conference. So I'll be speaking on inhomogeneous Ardha-Shreni random graphs. This is a joint work with Rajat Shubro Hajra of ISI Kolkata, Frank Den Hollander and Mateusz Fregara of the University of Leiden. So let me start with describing the model. So let f be a symmetric and continuous function from 0, 1 cross 0, 1 to the positive half line. Okay? And I fixed a sequence of numbers epsilon n, which goes to 0, but slower than n inverse. That is, n times epsilon n goes to infinity, and epsilon goes to 0. And I consider a random graph Gn on vertices 1 to n, where vertices I and j are connected with probability epsilon n f I by n j by n, okay, for all I not equal to j. So the probability of edge being present is not the same for all pairs of vertices, and hence the name inhomogeneous. Okay, if this was same, it will be called homogeneous Ardha-Shreni. And the choice is made independently for the different pairs of edges. So in other words, the graph that we get is simple and undirected. That is, there are no multiple edges or loops. And let n be the adjacency matrix of Gn. That is, there is 1 or 0 depending on whether there is an edge or not. Okay. So the other matrix associated with Gn that I'll be interested in is the Laplacian, which is essentially same as An except on the diagonals. Okay? So diagonals of An are 0 by definition. So what I do is on the diagonals I put the row sum. Okay? That's how I get the so-called Laplacian matrix. So I'll be talking about the limiting spectral distribution of both this adjacency matrix and Laplacian matrix. So that's the broad goal, to study the empirical spectral distribution of An and lambda after appropriate centering and scaling as n goes to infinity. Okay. So I won't be spending much time on this because this has been discussed several times today and yesterday. So these are the eigenvalues, and the measure which puts 1 over n mass at each is called the empirical spectral distribution. The first result is, as n goes to infinity, the adjacency matrix scaled by square root of n times epsilon n converges weakly in probability to a probability measure mu, where mu is compactly supported symmetric non-random probability measure on R. So by non-random I just mean that, so in An there are 2 levels of randomness. One is essentially the randomness due to the random variables, and then you pick an eigenvalue at random. So mu preserves just one of the randomness. Okay? So in other words, mu is not a random measure. So importantly, we don't need any centering. Or in other words, the centering, of course if you think of the elements of An, they have an expectation, but that's a smaller order than the centering. Okay? So An by square root of n times epsilon n converges to mu. So the same probability measure mu appears, okay, before that a small result. So this mu is absolutely continuous with respect to Lebesgue measure when the function fxy that's bounded away from 0. Okay. The measure mu arises as a limiting spectral distribution in several other contexts. I'll talk about one of them. So let xij be iid with mean 0 and variance 1, and I construct a matrix which is essentially a Wigner matrix, except that there's a variance profiling. So wn ij is square root of 1 over n f I by n j by n x I minimum j I max j. So if fi were I, this would have been nothing but a scaled Wigner matrix. Okay? So in that case also the limiting spectral distribution of wn would have been mu. So the same measure mu arises in other contexts. Another context is that of a random matrix whose entries are generated from stationary Gaussian process, okay? And there F plays a role in the covariance of that. I'm not going into that in this talk, but okay. An important special case is when fxy is Rx times Ry. So note that I haven't told you a description of the limiting spectral distribution. I just told you that such a thing exists, okay, without giving a description. And description is in a way complicated because we have used method of moments, and we can describe the moments and also the fact that the measure is determined by its moments, but nothing more. Okay? So thankfully, in some special cases, we have a better description. That is when fxy is Rx times Ry, okay, for some continuous function R. In that case, mu is the free multiplicative convolution of mu R and mu S, where mu R is the law of Ru, U being a standard uniform random variable, mu S is the standard semicircle law, and as I already told you, this is nothing but the free multiplicative convolution. Okay? So probably in this audience, there are several who know about free multiplicative and additive convolutions, but nevertheless I'll quickly go over a brief introduction to free probability theory, with apologies to those who are experts in this. So I start with a C star probability space. Okay. So C star probability space is an unital C star algebra. That is, it has a multiplicative identity and a function phi which is linear on A, and it is unital, that it maps the multiplicative identity to 1. Its threshold, that's phi of AB, is phi of BA, and it's positive, that is phi of A star A is greater than or equal to 0. An element of A is called positive if it's of this form, A star A. So for any element A in script A, its spectrum is just the collection of all those Z such that A minus Z times the identity is not invertible. And not invertible means it doesn't have a multiplicative inverse. So for a self-adjoint element A, spectrum is a compact subset of R, and furthermore, there exists a unique probability measure mu supported on the spectrum such that if you look at phi of A to the power n, that is given by the nth moment of the probability measure mu. Okay? So in other words, if you think of phi as an expectation and A as a random variable, then this is for this to be true, mu would have been the distribution of that random variable. Hence it makes perfect sense to call mu the distribution of A in this particular case also. So this is so this is analogous to the classical case with phi should be thought of as the expectation and A should be thought of as a random variable, except that we are now in a non-commutative setting. And the classical examples are n cross n random matrices. Okay, I won't spend much time on that. And then I define free independence. So two self-adjoint elements A1 and A2 are freely independent if for all choices of n and I1, I2, In in 1, 2 such that they necessarily alternate. Okay, that is Ij is not equal to Ij plus 1 for all j. You have phi of polynomials of Ai1 times polynomials of Ai2 times polynomials of Ain is 0 whenever P1 and P2, P1, P2, Pn are polynomial such that each expectation of each of them vanish. So if expectation of each of them vanish, then expectation of the product should vanish. So if this is true for all such choices, then I'll say A1 and A2 are freely independent. Of course, I mean this definition can be made for more than 2, but I mean the definition is analogous. So I'll just define it for 2. So if A and B are freely independent self-adjoint elements, then phi of any polynomial AB can be computed from the individual moments of A and B. Okay? In other words, so saying that A and B are freely independent is like a description of the joint distribution. Okay? So if you know the marginals of A and marginals of B, you can compute the joint distribution. So I'll just give you a trivial example. Let's say I want to compute phi of AB. So what I'll do is I write as A minus phi A times 1, B minus phi B times 1, and then I'll add whatever I have subtracted. Okay? And then free definition of freeness tells me that this A minus phi A times 1 has a vanishing mean, and so does this. So therefore, this just vanishes, okay? And then you can compute. So phi of AB turns out to be phi of A times phi of B. And this can be employed to calculate more complicated polynomials. So in other words, if you know all the moments of A and all the moments of B, in principle you can calculate any mixed moment of A and B. Okay. So if A and B are fully independent elements having distributions mu and nu respectively, then mu box plus nu is nothing but the distribution of A plus B. So this is known as the free additive convolution. And if one of them is positive, okay, then I can talk about A to the power half B, A to the power half, and then mu box times nu or nu box times mu, both are the same connotation. It's called the free multiplicative convolution of mu and nu. So this is the reason I put this in a slide, because I've already used free multiplicative convolution. Okay, and the same can be possibly done with measures with unbounded support, and I will be needing that towards the end of my talk, but I won't go into that. I mean, essentially you truncate and play a same game. So I'll just there's a word of caution that free additive convolution and classical additive convolution are not the same, and the same for multiplicative, excluding when one of them is degenerate. Okay, so this is the seminal result of Voiculescu, which essentially connects these two words, classical and free. So I've stated one of the most basic versions. I mean, it's true in much more generality. So I start with two independent Gaussian random matrices. So then W1n and W2n are asymptotically freely independent. That is, if you look at any polynomial P in two variables, then look at 1 over n expected trace of P W1n and W2n, that is same as phi of P S1 S2, where S1 and S2 are freely independent elements of some C-star probability space having a semicircular distribution. Okay? So by what I told you, you can actually calculate phi of P S1 S2 because you know that they're freely independent and you also know the marginals. So therefore you can use this to calculate the limiting spectral distribution of any polynomial of W1 and W2. Okay. So going back to our result, okay, so there are a couple of applications of that. So first one is a statistical application. So I consider a community of n individuals, okay, which I'll represent by vertices of the graph Gn. And I have data on whether an individual is acquainted with another. So an ideal example is a scientific community where acquaintance means whether two individuals have co-authored a publication or not. And my goal is to retrieve the sociability pattern of the community. So as stated, it's not even completely precise. So first goal is to make this question precise and then to be able to do the statistical application. So the way I model it is, we model the sociability distribution of the community by a probability measure rho on 0 infinity with bounded support. Okay? That means let R1, R2, Rn be Ayyer random variables, and these will be called the sociability index. That means the Ri is the sociability index of the ith individual. Okay? A high Ri means that individual is more sociable, and a low one means the individual is less sociable. Okay? So somehow, whether individual I and j are acquainted should depend on the index of both I and j. Okay? And one way of doing that is, it's on my next slide. So they are acquainted with probability epsilon n Ri Rj, where epsilon n is as before a sequence which goes to 0 but no faster than 1 over n. 1 over n is much smaller than epsilon n, is much smaller than 1. So once I've fixed epsilon n, there exists a state such that epsilon n Ri Rj is less than or equal to 1 for all ij, okay, because I assume bounded support for Ri's. So conditional on R1, R2, Rn, I assume that the ith and jth individuals were acquainted with probability epsilon n Ri Rj. And the data that is available is the adjacency matrix or matrix of acquaintances. So from that, somehow I have to get back rho. Okay? The statistical inference problem is to estimate rho from AN. Okay. So now, whatever I'm going to do, I'll tell you a way to estimate rho in principle, but I've never tried to implement it in practice, and there may be serious numerical issues with that. But it's just a starting point, and I'll tell you one way by which it can be done in practice, in principle. So for the sake of identifiability, I assume that rho has mean 1. Otherwise, what can be done is all the Ri's can be multiplied by 2 and epsilon n can be divided by 4. Okay? So to make the model identifiable, I'm imposing this assumption. So essentially, the scaling theorem, as presented at the very beginning, tells us that if you scale an by n times epsilon n to the minus half, then the empirical spectral distribution converges weakly in probability to rho box times mu s, okay? Where mu s is the Wigner semicircle law. So since we know an, in principle, we can estimate rho box times mu s. So there's one small problem in that, epsilon n is unknown, okay? So that has to be worked around by this. So if you look at square root of n by trace of n squared, then that helps us get rid of an, epsilon n. So this helps us estimate rho box times mu s. And in particular, what can be estimated are the moments of rho box times mu s, okay, by the law of large numbers. So rho box times mu s is a symmetric probability measure whose 2kth moment is a function of the first k moments of rho. Something more is true, that is, if you write this down as a function of the first k moments of rho, then the kth moment comes for the first time, the kth moment of rho comes for the first time, the 2kth moment of rho box times mu s. Okay? Therefore, the moments of rho can be recursively estimated from those of rho box times mu s. Okay? So if you know the moments of rho box times mu s, then you can recursively calculate the moments of rho. And since rho is a compactly supported probability measure, it is determined by its moments. So this is just one way of estimating rho. So the other application is in physics. So it's called the Gibbs ensemble. So I fix k1 star, k2 star, kn star. So I assume that the sequence k1 finite sequence is graphical, that there exists at least one simple undirected graph with this as degree sequence. And then I look at Sn, the set of all simple graphs of 1 to n. Okay? So this just ensures that this set is non-empty. So the Gibbs canonical ensemble is a unique probability measure on Sn with the following two properties. So look at sum over all g in Sn, kig times png. So this is nothing but if you choose a graph according to the probability measure Pn, then this is the expected degree of vertex I. Okay? The expected degree of vertex I should equal ki star for all I in 1 to n. Okay? And the entropy of Pn is nothing but sum over all g in Sn png log png. So it is nothing but expected value of log, negative expected value of log png. Okay? So I choose that Pn which maximizes this quantity among all probability measures on Sn, okay, which maximizes the entropy. So that is generating a random graph by that is called the Gibbs canonical ensemble. Okay. Sorry? It's unique. So we focus on the so-called sparse regime. So the maximum of ki star is much smaller than square root of n. as n goes to infinity. However, we also assume at the same time that ki stars are unbounded. Okay, so as n goes to infinity, the maximum goes to infinity. And then if you scale each ki star by mn and look at the probability measure which puts mass 1 over n on all of them, this is essentially a probability measure on 0 to 1 because I'm scaling by the maximum. So then I'm assuming that it converges to some probability measure rho. Okay? So that's another assumption. And then I denote by sigma n the sum of ki stars. So then a variant of the scaling theorem proved at the very beginning tells us that an with this particular normalization, you have to multiply by square root of sigma n and divide by mn times square root of n, converges weakly in probability to rho box times mu s. So this was actually one of the goals of starting this project. We wanted to understand this empirical spectral distribution of the adjacency matrix of the Gibbs canonical ensemble. Okay? And it turned out that it essentially has a multiplicative structure asymptotically. Okay? So we had to tweak the results in that way so that we could get this followed from our result. Okay. So now I come to the Laplacian. So once again, Laplacian is essentially same as the adjacency metric, except that on the diagonals I put a number which ensures that the row sum is 0. Row sum of the Laplacian is 0. So this can be thought of as a Q matrix of a continuous time random walk on Gn. So let Dn be a diagonal matrix whose ith diagonal entry is nothing but the expectation of the ith diagonal entry of the Laplacian. So the result is, if you center Laplacian by Dn, that is just you make the diagonal entries mean 0 and you divide by the square root of n times epsilon n, then its empirical spectral distribution converges weakly in probability to nu, again for some symmetric probability measure nu, which is no longer compactly supported anymore. So unfortunately, we don't have a description of nu in general. We could give a description only in the very special case of the multiplicative structure, okay, which I come to now. So if fxy has this structure rx times ry, then nu is the law of r to the half tu times ts r to the half tu plus a constant times r to the 1/4 tu tg r to the 1/4 tu, where alpha is this number. Tg and tu are commuting self-adjoint operators having respective distributions normal and uniform, and ts is a self-adjoint operator having the semicircular distribution which is freely independent of tg and tu. Okay? So after having looked at this slide, let's go back to the previous one. So now we understand what our tu, ts and tg are, so this is what nu is. Okay? So since there is this unbounded operator tg, so it has a Gaussian distribution, hence nu is also unbounded. The support of nu is also unbounded. Okay? So therefore, we can't do this on a C star probability space, but I'm not going into the details. I mean, there's something called affiliated operators, so this can be defined via that. So I won't give you a complete proof of this, but I'll tell you how does this finally come up. How does one get this as the limiting spectral distribution? Okay? I'll show that in the next few slides. So essentially it's an idea of proof. So without loss of generality, let us assume alpha is 1. Okay? So I write, so this is finally what we are trying to look at, delta n minus dn. So I write this as an minus diagonal n, where diagonal n is, so okay, so there's a typo here. So diagonal n is sum over j not equal to I an ij minus its expectation. Okay? So yeah, so I'm subtracting dn. Dn is the diagonal expectation of the diagonal entries of Laplacian n. So this should have been the mean corrected version of this. Okay? So sorry for the typo. Okay. So the first step is to replace the entries of the Laplacian by Gaussian random variables having the same mean, variances and the covariance structure. Okay? So this is possible by employing the Lindenberg Principle, which was further developed for random matrices by a paper of Saurabh Chatterjee in 2008. Okay? So that can be done. So we can essentially work with Gaussian random variables instead of the Bernoulli ones that we started with. Okay? The next important step in the proof is to decouple. Okay? So the way it's defined, the entries of diagonal, the dag n is are correlated with that of those of an. But the correlations are asymptotically small enough so that you can essentially replace them by a matrix which is independent of an. Okay? If you replace it, then the limiting moments are still the same. That can be calculated by method of moments. Okay? So that is the major step in the proof. So which I essentially sweep under the carpet. So once you grant these two steps, it's easy to see how that limiting spectral distribution comes up. So a slight bookkeeping will reveal that the entries of diagonal n are, the diagonal n essentially is a like square root of n times epsilon n, Rn times Gn, where Gn is a diagonal matrix with IID standard Gaussian entries, okay, and Rn is a deterministic diagonal matrix having a particular LSD. Okay, now we are dealing with Gaussian random variables, and hence this can be done. Okay. So you just have to calculate the variances, and this is what it turns out to be. And furthermore, this matrix Gn is independent of the matrix An I started with. So now, in other words, I can write n times epsilon to the negative half Laplacian minus the expectation of diagonal entries as Rn Wn Rn plus Rn to the half Gn Rn to the 1/2, okay, where Wn is a scaled Wigner matrix. Again, we just have to do the algebra correctly to get to this, modulo steps 1 and 2. And then Varkulis-Ku's theorem immediately tells us that Wn is freely independent of this tuple Rn and Gn. So remember, Rn is a deterministic matrix, Gn is a matrix independent of Wn. Okay? Wn being a Wigner matrix, it's freely independent of this tuple. And therefore, we immediately write that the empirical spectral distribution of the Laplacian converges to the law of R times S times R plus R to the half G R to the half, where S follows a semicircular distribution which is freely independent of the pair R and G. G follows standard Gaussian because G is essentially the limit of Gn, and the elements R and G commute. Okay. So in other words, this essentially describes completely the joint distribution of S, R and G. Okay? The moment you assume S is freely independent of RG, you can calculate anything which involves S and R and G, and you know R and G commute. Okay? So you can calculate any mixed moment of S, R and G. So this is how this comes up in the limit. Okay. So there are several directions in which we plan to take this. So one is study the largest eigenvalue of the adjacency matrix. So one of our students, Shukrit, who is in the audience, he is working on this. Okay, in the next slide I'll tell you conjecture in that regard. So the other important direction is study the second largest eigenvalue of the Laplacian matrix. So the way we define it is the largest eigenvalue is always 0. So hence the second largest value is of importance. So the modulus of the second largest eigenvalue, so which is known as the spectral gap, this has implications for the random walk on Gn. So for example, if the second eigenvalue is non-zero, then the graph is connected. So proving that happens with high probability would have a serious implication for the graph. And a close relative of the model we studied here is the configuration model, and for that also several of the questions stated above are open. Okay, so that's another possible direction for future work. Okay. So like I told, Shukrit is working on the largest eigenvalue, okay, and he has made some progress in that direction. So, but the most general conjecture is that if lambda n is the largest eigenvalue of an, and epsilon n is somewhere between n to the negative 2/3 and 1, then lambda n minus theta times n times epsilon n minus a constant Cn that scaled by epsilon to the 1/2 converges to z, where z follows normal 0 sigma square. Okay? And Cn is something which converges to a finite constant, okay, where this theta, c and sigma square are finite and positive constants. So we have got results for special cases, but we are yet to reach here. Okay, so these are the two references. So since I have some time, I can actually spend some time telling you at least what theta is. Okay? So again, this is only at the level of the conjecture. So lambda n is the largest eigenvalue of the adjacency matrix An. Okay, and if you look at An, the entries of An they don't have mean 0. Okay, they have expectation of An is essentially, so Anij follows Bernoulli with right. So what we do is we write An as An minus expectation of An. So this is a matrix plus expectation of An. Okay? And this, after scaling, behaves more like a Wigner matrix, whereas this is a deterministic matrix. Okay? And the largest eigenvalue actually comes from this matrix. The largest eigenvalue of this beats that of this. So the largest eigenvalue essentially comes from this matrix. So this is, if you think of this function f as an operator on L2, essentially the right endpoint of the spectrum of that. So that's theta.